Hello students. In the last class we have learnt about natural numbers, whole numbers, integers and rational numbers. We found numbers between two rational numbers, decimal representation of numbers, and we have also done types of rational numbers, terminating and non-terminating but repeating decimal representation. Now the objective for today is conversion of rational numbers into decimal form and irrational numbers. We are also going to see some useful results based on irrational numbers. Let us begin. In the past class, we left at pure recurring decimal numbers. So the pure recurring decimal numbers were of the form 0.2 bar, 0.635 bar, which means all the digits after the decimal points were recurring, were repeating. For example, 0.2 we can write as 0.2222. 0.635 bar can be written as 0.635 and so on and so forth. Now these are called pure recurring decimal numbers. Today we will first understand what is mixed recurring decimal numbers. Now suppose if you have a number of the form 5.23 bar and the bar is at 3. So what does it mean? It means that we have to write it as 5.23333. Now if you have to solve or if you have to convert a pure recurring decimal digit, we had learned that we just need to write as many number of nines in the denominator as there are number of digits. For example, 0.2 can be simply converted and written in a fraction form as 2 by 9. Similarly, if we have to write the decimal number 0.635, we have to convert it into rational number. We will write 635. We will count the number of digits, which in this case is 3, and we are going to write 999. Now let us understand how to convert these mixed recurring decimal numbers into rational numbers. Let us first take an example where we have the number 5.2 bar. Here this is also in mixed form. Why? Because we have 5 which is non-recurring, which has no bar on it, and then we have a decimal number after that. 5.2 can be simply written as 5 plus 0.2. Similarly, 5.2 bar can also be written as 5 plus 0.2. The only difference will be there will be a bar, which means 2 is continuing. So what we can do is we can write 5.2 bar as 5 plus 0.2 bar. Now 5 plus 0.2 bar is equivalent to 5 plus 2 by 9. Why? Because we have already learned that 0.2 bar is equal to 2 by 9, and so we will get here 45 plus 2 by 9, and that is equal to 47 by 9. This is a simple way of doing it. You can directly get the result. You divide the number between the number and the bar, and then you simply write the rational number, corresponding rational number. The other way or the proper way of doing it as given in your books is let x is equal to 5.2 bar, and we will consider this equation as equation 1. We will multiply both sides by 10. This will give us 10x is equal to 52.2 bar. We will count this equation as equation 2. Subtract 1 from 2. We get 10x is equal to 52.2 bar. X is equal to 5.2 bar. 2 bar will get cancelled. We will get 0 here, and here we will get 47. Here we get 9x. So 9x is equal to 47 and gives us for x is equal to 47 by 9. So this is the way we usually do as per our books. At the same time, you can check whether your answer is correct or not by simply putting it as 5.2 bar, which we have discussed earlier, is equal to 5 plus 2 by 9, and you will get 47 by 9, which means your answer is correct. Let us take one more example. We have the number here 23.43, and the bar this time is on both the numbers. Again, let's try with the direct method. This can be written as 23 plus 0.43 the whole bar, which means 23 plus 43, and there are 2 digits, so we'll divide it by 99. 23 into 99 plus 43 by 99. we get as 2320 by 99. Now if we will solve it with our proper method, we should get the same answer. Let us see. X is equal to 23.43 bar. I am assuming that you will do the steps yourself and those steps will be correct. So we'll have to write here, let X is equal to 23.43 bar. The sentence will be multiplying both LHS and RHS by 100. Why we are multiplying it by 100? Because we have two digits and that will give us 100x is equal to 2343.43 bar. This will call as 2. Subtracting 1 from 2, we get 99x is equal to 2320. X is equal to 2320 by 99. If you remember, the same answer we had got by our direct method as well. 23.43 bar is equal to 23 plus 0.43 bar, which means 23 into 99 plus 43 divided by 99, and we got the same answer as 2320 by 99. So we can say that this is the correct answer. This is one method of checking whether the answer that you have received is correct or not. Now let us take one more example. In this example, the bar will be only at one digit after the decimal point. So our question is 4.32 and the bar is only at 2. How will you do this kind of question? So in this kind of question, you will have to first write, let X is equal to 4.32 and the bar is at 2 only. We call this equation as first equation. First, what we need to do in this is you just have to apply a little trick. You will have to bring this particular number, which does not have recurring decimal, on the left hand side. You will have to bring it on the excess side. So what we need to do? We need to multiply this one digit. So it is only one digit. So we need to multiply it with 10. Multiplying 1 with 10. What do we get? We get 10x is equal to 43.2 bar. So 10x is equal to 43 plus 0.2 bar, which means 43 plus 2 by 9. This gives us 43 into 9 plus 2 divided by 9, and hence x is equal to 389 by 9. 10x is equal to this implies x is equal to 389 by 90, and this is your answer. So this is again another way of doing, in this you just have to bring those non-recurring parts on the left hand side, and then you have to use the direct method and you can get the answer. Let's try to solve one more problem. The problem here is 0.621 and the bar will be only at 1. So how we will do it? We'll just quickly run through it. We will write x is equal to 0.621 bar, and there are two digits, so we will write 100x is equal to 62.1 bar. Now we know that this can be written as 62 plus 0.1 bar, which means 62 plus 1 by 9. Now you can multiply 62 into 9 plus 1 divided by 9. Bring both the hundreds here. 62 plus 9 into 9 plus 1 by 9 into 100, and you have to solve this and you will get your rational number. So I hope you have understood this method as well. Till now we have learned and understood that rational numbers can be expressed either in terminating decimal form or in non-terminating recurring decimal form. So if it is non-terminating, it has to be recurring, and it is very easy to understand. 0.2, only thing you need to remember is 0.2, which means only one bar is there. You can directly convert it as 2 by 9. If it is 0.35, you can directly write it as 35 by 99. And if you have understood this part, other parts are quite easy. This is the first kind of question we did. Now the second kind of question that we did was 5.32 bar. In this kind of question, we split it into 2 and we write 32 by 99, and then we multiplied 99 into 5 plus 32 divided by 9, and whatever is the answer you can write. This is again one form of question. And the third form of question we did was where the bar is only on one digit. In this case, what we did, we brought the non-recurring digit on the left hand side, which means 10x is equal to 53.2 bar. We have to multiply both x. Here we have to suppose that this is x, and we will have to multiply both LHS and RHS with 10. We get 53.2 bar. Now implies 10x is equal to 53 plus 2 by 9. You can simply run it just like the second case, plus 2 by 9, and x, the 10 part will come down and this will become, and when you will solve it, you will get the answer. These are the three things which you have understood, and with this we complete our portion where we have to understand how to convert a decimal number into a rational number. Let's start with irrational numbers. A number is an irrational number if it has a non-terminating and non-repeating decimal representation. So in rational numbers, we have seen that either they have terminating decimal representation or repeating decimal representation. Irrational numbers are not of the form p by q. So they are not like rational numbers. They do not exist in the form p by q where p and q are part of integers. Yes, they do exist on number line. Some of the examples of irrational numbers are under root 2, under root 3, under root 5, under root 7. In fact, any under root n where n is not a perfect square. The question asked in this particular section is prove that under root 2 is not a rational number. Similarly, you may get questions like prove that under root 3 is not a rational number, under root 5 is not a rational number, under root 7 is not a rational number, or under root n where n is not a perfect square is not a rational number. So these kind of questions are usually asked in this particular section. We will first begin with this and we'll see one more example. So to prove that under root 2 is not a rational number, there are two ways of doing it. First way is something that you have studied in class 8, which is called long division method. This is a simple way of doing it. You just need to keep on dividing and then multiplying it with twice the number, and then you need to find the result. For example, here we will take 2.00000000. We are going to apply long division method. So the first number we are getting is 1. We'll put 1 here as well. We get 1. Then we bring 2 zeros down. Here we put a dot. We multiply this 1 and into 2, and then we write here 4. Here also we write 4 and we get 96. Again we bring 4 down, 400. So we get twice of 14 is 28, and we write here 1. Here also we write as 1. We get 281, and then 119 is the remainder. We bring 2 more zeros down. Here 141. So twice of 141 is 282, and here we'll write 4. Here also we'll write 4. We get 11296. Remainder is 604. Again we bring 2 more zeros down. We write here 2828, and then we multiply 2, and here also we write as 2. 56564. So we get 383, and this will continue. So we can safely say that under root 2 is equal to 1.4142, and we see that the numbers are not repeating and the decimal numbers are not even getting terminated. So this is not a rational number. This is one way of doing it. This is the first way of doing it. The second way is called method of contradiction. In method of contradiction, what we do is we assume whatever has been asked for, we will assume that that particular condition will apply. For example, it is said that you have to prove that root 2 is not a rational number. So we will say that okay, let us assume that it is a rational number. But since we are saying that let us assume, we will say if possible. Why if possible? Because it is actually known that under root 2 is not a rational number. So we'll say if possible, let us assume that under root 2 is a rational number. Then under root 2 is equal to p by q, where p and q are integers and q is not equal to 0. Now let us square both sides. We get 2 is equal to p square by q square. What does this mean? This means that p square is equal to 2q square. This implies that p square is an even integer. This further implies that p is also an even integer. Now you might even ask, p square is an even integer, then why is p even? For that, let us assume that if p is not even, we know that it will be of the form 2m plus 1, where m is again an integer. Now this means that if we will square it, we'll apply that formula a plus b the whole square, and we'll get 4m square plus 4m plus 1. And plus 1 means that it is odd, which means p square is odd, because when p was odd, p square also became odd. This is contradiction because we have found that p square is even. Now suppose p square is equal to 2q square, that is equation 1, and we get the second equation as p is an even integer. Now let p is equal to 2m. Why? Because we know that p is an even number, and since p is an even number, it will definitely have 2 as its factor. Again, we'll square both the sides. We get p square is equal to 4m square. From 1 and 3, what do we get? We get 2q square is equal to 4m square, which means q square is equal to 2m square. This implies that q square is even, and hence q is also even. Now what we have found? We have found that p is an even integer. Similarly, q is an even integer, and let us call this equation as equation 4. From 2 and 4, what do we find? From 2 and 4, we find that p is even, q is even, so they have a common factor. P and q have a common factor. Now since they have a common factor 2, if you remember, we have stated it quite a few times that rational numbers are always in their lowest form and they cannot have a common factor. Hence, we derive this that root 2 is not a rational number, it is an irrational number, and we obtain it with the help of method of contradiction. Now let us prove that under root 5 is not a rational number. One you can do with long division method, and that is known to you. Other method of contradiction we are going to do now. So same steps we are going to write. If possible, let under root 5 be a rational number. Then what will happen? Then root 5 is equal to p by q, where p and q are integers and q is not equal to 0. Now again, p by q are in the lowest form and they should not have any common factor. Squaring LHS and RHS, or in simple terms we usually write squaring both sides, we get 5 is equal to p square by q square. Let this be first equation. We get, this implies that p square is equal to 5 q square, which means 5 is a factor of p square, implies 5 is a factor of p as well. Now to validate this, we'll take a few examples. Suppose we have a number p square. The value of p square is 25. Now in this case, 5 is a factor of 25 and p is equal to 5. 5 is a factor of 25. 5 is also a factor of 5. Similarly, you can take p square as any other number which has a factor 5. Let's take 625. 625 is equal to p square. Now 5 is, so 625 has factor as 5. P is equal to 25. P also has a factor as 5. So we can say that, when 5 is a factor of p square, or any number is a factor of p square, then that particular number is also a factor of p. Now let p is equal to 5m, because p is a factor of 5, so any number will be multiplied to it, multiplied to 5. Now again, p square is equal to 25m square. We are squaring it. So what do we get? So our equation was this. Here we will substitute p square is equal to 5q square, and we get 5q square as 25m square, which means q square is equal to 25m square by 5, that is equal to 5m square, implies 5 is a factor of q square, implies 5 is a factor of q. This means they have again a common factor. This contradicts our assumption that p by q have no common factors, which means they are rational numbers. So under root 5 is an irrational number. It is not a rational number. Those statements you will have to make here. Similarly, we can take any number n which is not a perfect square. You can take any number, say for example 62. 62 is not a perfect square. So you can prove that it is an irrational number. What we need to do? First we need to square. For example, p square by q square is equal to n, and then we need to p by q is equal to n, and p square by q square is equal to n square, and we have to write it as p square is equal to n square q square. So n is a factor of p square, implies n is a factor of p. Similarly, you can substitute and you can write, let p is equal to nm, implies p square is equal to n square m square, implies nq square is equal to n square m square, implies q square is equal to nm square. Now they have a common factor again, n, and hence they cannot be rational numbers. Root n has to be an irrational number. So we'll stop our class here. In the next class, we'll see some useful theorems on irrational numbers. Thank you for watching. If you have gained any knowledge, please do like the video. Thank you.